Hello everyone, I welcome you all in this lecture. So in this lecture, I will start aircraft inertia load. So this comes under the airframe load only. So why this is important? Because see, according to the Newton first law, if body is in rest, it will try to remain in rest, and if body is moving, it will keep moving unless if you apply any external force. That means you can say aircraft will experience maximum amount of load during the acceleration or deceleration. So keeping this in mind, we will cover the aircraft inertia load. So let's say body is moving, if you are trying to apply the brake, it will try to resist. I mean to say, if you are applying any kind of backward motion, it will try to resist and try to move in a forward direction. So there the inertia plays a very important role. So you can see that you can take a two axis x and y, and you can take origin as a O, and you can denote elemental mass delta m at a distance r, which is having angle theta from the horizontal, and cg somewhere here, x bar y bar. So this according to when the body is rotating, the centripetal force will be in this direction, right? So what will be the inertia force? Opposite to that one. So that means delta m r omega will be outward direction. So you can resolve into 2 omega square x delta m and omega square y delta m. So you can write fx equal to under root omega square x into delta m and fy equal to omega square y into delta m. And since omega is constant, so you can take it out, integral x delta m and integral y delta m, fx and fy. So the thing is clear why I am writing fx and fy. Two forces, right? You are resolving r delta m omega square, and you know that m r omega square is a force, right? Centripetal force. But this is the inertia force, opposite to that one, right? So that's force m r omega square acting inward, but inertia for m r omega square will be outward. And here m is delta m only. You are talking about the elemental mass, right? So basically, what integral x into delta m you can denote as a x bar, and fy equal to omega square m y bar. So consider the case 1. If CG lies on the y-axis. So if CG lies on the y-axis, that means what? If CG is on a y-axis, x is 0, right? That means x bar equal to 0, so fx equal to 0. And similarly, if the CG lies on the x-axis, that means y1 0. Y will be 0, so y bar equal to 0. So fy equal to 0 from this, right? Consider a rigid body. That means when you are applying force, the particle is inside the body is not getting displaced. So you can take same delta element mass here, but now is apart from omega you will have a alpha angular acceleration. So the angular acceleration will be what? Let's say r delta m, and you can divide r alpha delta m sine theta and r alpha delta m cos theta. This two direction, right? Because that angular acceleration is in this direction, right? So the force uh, r alpha delta m will be in this direction only. So you can write force fx equal to integral y delta m and fy equal to minus x delta m. Why minus? Because this is positive, but this force is in negative direction. That is why fy is written negative. So okay, this part alpha m you can take it outside. Integral y dm y bar and integral x dm x bar, but minus sign is coming here because of the direction is downward, right? And if you multiply by the distance r, you will get actually torque. So R into R become R square, and if you integrate you will get total tau, total torque integral R alpha R square delta M. So R square delta M you can take it one side, and what is R square delta M is mass moment of inertia, integral R square delta M. So mr square, right? And this is an I naught. You can write a moment of inertia about the CG, and plus mr bar square. This is using parallel axis theorem. R bar is nothing but the under root x bar square plus y bar square. So that means you have some distance, right? You have a distance, right? The distance x bar and y bar is located, right? So you can write torque I naught alpha and substitute I naught. So this will be the expression of a torque. Alpha will multiply here I Cg alpha plus m alpha x bar square plus y bar square. So I thought it's better to cover the simple force and torque, so that you will when I will take the example problem, then you will be able to understand uh, the inertia force. Now consider this example. This is plain. Then let's say if I want to know the significance of inertial force, it will be good to have some kind of practical example and try to understand. So I have taken a, let's say, one aircraft model, let's say F-18 aircraft model, and since in a normal runway when you land you have a sufficient length, right? Let's say for example this kind of aircraft 1.5 kilometer to 2 kilometer runway is required, easily it can land, okay? And for if you want to land on a ship deck, that means that much length will not be there to land. So that means some kind of resistance or some additional resistance you will try to provide. Although aircraft has a spoiler etc, brake also in the wheel, but in addition to this you have to apply something more to reduce the landing distance. So when you are trying to apply more brake, more inertia force will be there. That exactly we will do in this numerical example. So what we will do? So you can see that the rope will be put on the hook that will provide the resistance, and this way you can actually stop there. You can see the arrestor hook is there. So I request you go and see how the ship deck landing is performed. So you can see there is a wheel, so R will be the reaction, and this is a CG point, so weight will be acting downward, and you have a one reference line, futurized reference lines. From that you are taking an angle lambda. So this is not, it is less than 90 only, because exactly 90 degree you will not put that. In that case you will have a lot of load during time of landing, and the landing may break. Okay. So what is MA? Basically when you are applying this uh, through the cable you are providing the resistance, and you are attaching this cable into the hook here, and the force is in this direction. So that means inertia force M into A will be in this direction. That is how M is written. M is a inertia force. In this case, if something is weak here, for example, let's say this part, this part, this part, so the whole structure may break. That is the importance of significance of inertia. Inertia is more, structure is weak, then it may break from here, wherever it will feel it is weak, right? So that is why I have taken one cut section. In this we will see how, what kind of normal and shear load is acting. Okay, if it is more, then it is good that keep more resistance is getting offered by this portion. That mu is this angle making with the horizontal, this reference line, and lambda is angle already told. T is a tension in the cable, A is the aircraft acceleration, W is the aircraft weight, CG is the center of gravity. I think nomenclature is clear, right? And this is the tail part. So if I balance the force in a horizontal direction, then Ma minus T cos mu will equal to 0. Please see this. I am resolving my force along this direction, and this is a t, this is mu, that is why t cos mu is written, because you have to resolve along this direction. Please take a pen and paper and try to do this, and if you have any doubt, please ask. So ma minus t cos mu equal to 0. So one component will be t cos mu, another component will be t sin mu, which is r minus w minus t sin mu. So t sin mu will be act downward, w is acting downward, r is acting upward. So that is why the balance is r minus w minus t sin mu equal to 0. This is two equation. Now when you cut this section, you have a separated tail part. So let's say empty is the tail portion mass. Empty with it will have some kind of 10 percentage of total aircraft weight, or 15%. That is why I have written W by K equal to M into G. Okay, some factor. Okay, so let's say I will give you the numerical value of this. So okay, now when you cut the section, you can take the axial load. So axial load you can resolve in axial direction, n minus t plus mt a cos mu minus mtg sin mu equal to 0, and shear load will be m minus mt a sin mu minus mtg cos mu equal to 0. Please see here, n I am taking in this direction, t is opposite to that, that is why n minus t is written, and this is mta, so one component along this plus mt cos mu. Okay, so that is why I have mta cos mu I have written, and gravitation force will also acting downward, mtg sin mu will be there. Okay, and for shear, s minus mta sin mu, because this is a mta cos mu, this is a sin mu. Okay, downward direction, and one component is sin, another component will be mtg cos mu. Okay, downward. That is how I have written equation 3 and 4. Now let's say the F-18 HAR model I have taken, because this is a very famous aircraft, US Navy aircraft. So M is 16800 and MT I have taken, let's say, divided by 10. So I have taken approximately 10 percentage of a total mass, which is the mass of the tail, which you have cut the section, right? Tail portion, also called empennage, vertical tail and horizontal tail, and some part of the fuselage also. Lambda 75, mu equal to 5 degree, a equal to 2g. Okay, so if you want to do I mean to say what kind of load acting on a wheel, I mean to say related to r, you can take a lambda, otherwise lambda is not used here. Okay, so in equation 1, if you put all the value, you will get t equal to 337 kilonewton, and from equation 2 you will get r equal to 197.396 kilonewton. So t and r you got, and then you can in equation from equation 3, if you substitute all the value, you will get n equal to 305 kilonewton, and from equation 4 you will get, if you substitute all the value, you will get s equal to 19.665 kilonewton. You can see this n is much more than compared to the uh, s value. So because body is moving in that horizontal direction, right, and inertia force in horizontal direction, right, so that is why you can see that key n is much more than compared to the s. Now what I told in the beginning, the runway requirement length will be like, let's say for example 1.5 kilometer to 2 kilometer, but here you take this case, v square equal to u square plus 2as, so final velocity is 0. Let's say 72 is a landing speed, let's say something, you can take a landing speed 1.1 times or 1.15 times or 1.2 times v stall. So let's say 72 is a touchdown speed, so 72 square minus, this is a realistic speed, 72 square, and minus acceleration is 2g, so minus 2g, because deceleration is there, right, that is why you have put minus sign. So h is coming 129.6, so you can see from 1.5 or 2 kilometer, the distance is reduced to 129.6 meter only. And because of what? Because of that hook which you are with the cable which you are using and fitting in the hook and try to resist the aircraft motion. That is how you reduce this distance to 129.6 meter. So in this case there will be large amount of inertial load will be there. I discussed so many N, S. Okay, you can check MA. So if inertia force is more, you have to be more careful about the structure point of view, because large acceleration and deceleration, at the beginning of the lecture I told that key, in that case aircraft component will experience large load, maximum load, and if your aircraft is not strong enough, the structure may break. Okay. So we'll take one more example, rotational case. You can see this is a one wheel, nose wheel, and another wheel is this. You have a one force m into x in this direction and downward m into az. That means let's say if aircraft is landing like this, so this moving forward also and downward also, and you have a moment about CG my, and ZCG is this, and since this wheel is touching to the ground, so there will be friction in this direction, right? And you take a reference rear landing gear and nose landing gear XR and XN, and W equal to 250 kilonewton, ln equal to 0.5, XR equal to 0.5, and ZCG equal to 1 meter. What is ln? Ln is what the nose wheel has a position above the ground, ln. So let's say this friction force is 400. So if you balance horizontal force, max equal to 400 kilonewton. So x equal to 400 by 25, right? W is 250 kilonewton. That means if you divide by 10, that means G, you will get 25, right? So 16 meter per second square will be the Ax. And in vertical force, you will see 1200 MAZ plus W. So MAZ is acting downward, W is acting downward, and vertical force is 1200 kilonewton. So you can write this equation: 1200 kilonewton equal to MAZ plus W. So you substitute all the value, you will get AZ equal to 3.8 G. And if you try to balance the moment, this force is what? 1200 Newton into XR and 400 Newton into ZCG. That is exactly I have written 1200 Newton into XR plus 400 Newton into XG. That will come around 100 kilonewton meter. And that moment I already explained at the beginning of the lecture, M equal to Y alpha, right? So alpha will be my by I. So alpha will be 1.6 radian per second square. I you can take 6 into 10 to the power 5 kg meter square. So you can find out alpha 1.6 radian per second square. And let's say initial vertical velocity is 4 meter per second. So you can see final will be 0. So 4 minus 3.8 into 10 into t. So you will get t equal to 0.1 s. So from omega equal to omega naught plus alpha t, since you know that u equal to u naught plus at, right? So in rotational case, omega equal to omega naught plus alpha t, where omega is the initial angular velocity and omega is the final angular velocity. Initial is 0, alpha you have found out 1.6, t 0.1, you will get 0.16 radian per second square. So from this actually you can actually feel that ki what kind of angular acceleration we are getting, what amount of time you require. I mean to say aircraft is pitching from, let's say, 0 degree to 10 degree. If it is very fast, you have to control, right? So this way you can actually feel the inertia part in a rotational motion also. So we have covered the fundamentals of inertia load, and then we have taken the example of one ship deck landing, and another just for translation motion, and second one is for rotational motion. Okay, so I request take some another aircraft also and try to do the similar exercise, And if you have any question, then please ask me. I will try to answer your question. Okay, thank you so much. We'll meet in the next class.